Every step can show a hidden sign. For people with Parkinson's disease, small change in walking patterns may appear earlier, but they are not always easy to detect through short clinical observation. I am Wong together with Mohamad Fitri and Shankari Nair under the supervision of technologist Dr. Haji Zunuwanas bin Mohamad. Today, we present our innovation, Gait AI, developments of a wearable IMU-based gait analysis system for Parkinson's disease early detections using machine learning.
Parkinson's disease is progressive neurological disorder that affect body movement, balance, posture, and walking patterns. One of the early signs that can appear is gait abnormality, such as slow walking, irregular step, reduced movement, or poor balance. However, early gait changes are sometimes difficult to detect through normal observation. Current assessments are often done in clinics using visual observation or clinical scoring, which can be subjective and limited to a short testing time. Advanced gait analysis systems are available, but they are usually expensive, bulky, and not suitable for simple daily screening. Therefore, there is a need for a low-cost, wearable, and easy-to-use system that can collect its gait data objectively and support Parkinson's disease early detection.
So the main objective of this innovation is to design a wearable bilateral knee-mounted IMU system using MPU 6050 and ESP32 for real-time gait data collection and IoT transmission. So this project also aims to develop a machine learning model for Parkinson's disease early detection based on IMU gait data and integrate it into a web-based platform. At the same time, the system performance is evaluated in terms of accuracy, reliability, and also effectiveness. So overall, the objective is to create a simple, affordable, and data-driven gait analysis system that can support early Parkinson-like movement screening.
The novelty of Gait AI is the integration of wearable IMU sensing, IoT data collections, and machine learning analysis into one complete early detection system. Based on the literature review, many existing systems are either complex, use multiple sensor placement, focus mainly on thermals, or do not fully connect sensor data with a web-based machine learning platform. In comparisons, Gait AI use a practical bilateral knee mount design. The MPU 6050 collects knee movement data, while the ESP32 sends the data wirelessly to Blink and Google Sheets. The data is then uploaded to the Gait AI website, where gait features such as acceleration, step frequency, movement patterns, and frequency features are extracted. Several machine learning models were tested. The best model selected for this system is the Artificial Neural Network, or ANN. This makes Gait AI not only a wearable sensor device, but also a complete IoT and AI-based gait analysis platforms for Parkinson's disease early detection.
Alright, now let me show how Gait AI is used. First, the user wears the knee guard. The MPU 6050 sensor unit is attached securely to the knee guard using a Velcro strap positioned slightly above the knee. Once the device is fixed properly and the user is standing in a ready position, we open the Blink application and press the Start button. As the user starts walking, the ESP32 collects knee movement data from the MPU 6050 sensor. The live acceleration values can be observed in Blink, so we can confirm that the sensor is working and the data is changing. At the same time, the data is sent directly to Google Sheets, where every new walking session creates a new tab automatically. After the session is completed, we download the data as a CSV file and upload it into the Gait AI website under the registered user profile. The website then processes the gait data, extracts important features such as acceleration, cadence, step frequency, and movement pattern, and analyzes it using our trained artificial neural network model. Finally, the system shows whether the gait is normal or Parkinson-like, together with the confidence score and summary.
Gait AI has strong commercialization potential because it is developed using low-cost and commercially available components such as ESP32, MPU 6050, knee guards, and web-based platform. The system can be marketed to clinics, rehabilitation center, early care center, community health program, and home care user. It is especially suitable for early gait screening, rehabilitation monitoring, and follow-up assessment for users who may show Parkinson-like movement symptoms. Another advance is that the device is portable and does not require expensive gait laboratory equipment. This product can be commercialized as a complete wearable screening device or as a service package with access to the gait AI website, user management analytics, and downloadable reports.
The impact of Gate AI can be seen in three main areas: users, healthcare workers, and digital healthcare development. For users, it provides a simple, wearable, and non-invasive ways to check gait patterns. For healthcare workers, Gate AI provides objective gait data, confidence scores, and downloadable reports to support early screening and clinical reference. For healthcare centers and community programs, it offers a more affordable and portable alternative to expensive gait laboratory systems. Overall, Gate AI supports early awareness, reduces dependence on manual observations, and promotes wearable technology and machine learning in healthcare.
In conclusion, Gait AI is designed to support Parkinson's disease's early detection through wearable gait analysis and machine learning. By combining MPU 6050 sensors, ASPTT2, Blink, Google Sheet, and an ANN-powered web platform, this innovation transforms simple knee movement data into useful gait analysis results. It is low-cost, portable, easy to use, and suitable for early screening support. In line with the theme, Unlocking Tomorrow Had the Impossible, Gait AI show how wearable technology and artificial intelligence can make future healthcare screening more accessible, practical, and data-driven.